Hello everyone. Welcome back. In today's presentation, we are going to discuss one of the most important hydraulic concepts associated with reciprocating pumps acceleration head. If you have ever worked with reciprocating pumps in the oil and gas industry, chemical plants, power plants, or water treatment facilities, you know that these pumps behave very differently from centrifugal pumps. Their flow is not continuous. Instead, it is pulsating because the piston continuously accelerates and decelerates the liquid during every revolution. This repeated acceleration and deceleration creates an additional pressure requirement inside the suction and discharge piping. We call this additional pressure the acceleration head. Understanding acceleration head is extremely important because it directly affects pump suction performance, cavitation, net positive inlet pressure, pipe sizing, pulsation, vibration, overall pump reliability. In this presentation, we will first understand how a reciprocating pump works, then learn why acceleration head develops, how it changes during the piston motion, what factors affect it, and finally discuss practical methods used by engineers to reduce its effects in industrial applications. By the end of this presentation, you will understand not only the theory but also how this concept is applied during pump design according to API standards. So, let's begin. Hello everyone. Welcome. Before we study acceleration head, we need to understand the basic operating principle of a reciprocating pump. A reciprocating pump belongs to the category of positive displacement pumps. Unlike a centrifugal pump, which transfers energy continuously through a rotating impeller, a reciprocating pump physically traps a fixed volume of liquid and pushes it forward during each stroke. The pumping element may be a piston, plunger, or diaphragm depending on the pump design. Let's understand the working principle. Imagine a cylinder with a piston inside it. When the crankshaft rotates, the piston moves backward. This movement increases the cylinder volume and creates a pressure lower than the suction pressure. As a result, the suction valve opens automatically, and liquid enters the cylinder. This is called the suction stroke. Now, as the crankshaft continues rotating, the piston starts moving in the opposite direction. The liquid inside the cylinder is compressed. The suction valve closes. The discharge valve opens. The trapped liquid is forced into the discharge piping. This is called the discharge stroke. Since every stroke displaces a fixed quantity of liquid, the flow rate is almost independent of discharge pressure. That is why reciprocating pumps are capable of generating extremely high pressures while maintaining accurate flow delivery. This makes them suitable for applications such as high-pressure chemical injection, boiler feed systems, hydrostatic testing, reverse osmosis plants, oil and gas production, slurry transfer, and many other industrial services where precise flow control is required. However, because the piston continuously starts and stops during every revolution, the liquid inside the piping also accelerates and decelerates continuously. And that is exactly where the concept of acceleration head begins. Now let's look at the different types of reciprocating pumps commonly used in industry. The first type is the single-acting pump. In this design, pumping occurs only during one side of the piston movement. For example, liquid may be discharged only during the forward stroke, while the return stroke simply fills the cylinder again. This design is mechanically simple but produces highly pulsating flow. The second type is the double-acting pump. Here, both sides of the piston are used for pumping. While one side performs suction, the other side performs discharge simultaneously. As the piston reverses direction, the operations interchange. Because discharge occurs during both strokes, the flow becomes much smoother compared to a single acting pump. Next is the plunger pump. Instead of a piston sliding with sealing rings inside the cylinder, a plunger moves through stationary packing. This arrangement allows much higher operating pressures because the sealing system experiences less wear. Plunger pumps are extensively used in refinery services, offshore platforms, high-pressure cleaning systems, and chemical injection packages. Most of these pumps are designed according to API 674, which is the international standard for reciprocating positive displacement pumps. Finally, we have the diaphragm pump. Instead of directly moving the liquid with a piston, a flexible diaphragm deforms and displaces the fluid. Since the liquid remains completely isolated from the mechanical components, diaphragm pumps are ideal for toxic chemicals, corrosive fluids, acids, hazardous liquids, and pharmaceutical applications. These pumps generally follow API 675, which covers controlled volume metering pumps. Although all these pump types have different construction, one thing remains common. The liquid inside the piping continuously accelerates and decelerates during every pumping cycle. Therefore, all reciprocating pumps experience acceleration head. Now we arrive at the most important concept of this presentation. So, what exactly is acceleration head? Acceleration head is the additional pressure head required to accelerate the liquid inside the suction or discharge pipe during the piston motion. To understand this better, imagine a long suction pipe completely filled with water. When the piston suddenly starts moving, the water inside the pipe cannot instantly reach the required velocity. Why? Because water has mass, and any object having mass possesses inertia. According to Newton's second law, force equals mass multiplied by acceleration. Therefore, whenever we want to accelerate a mass of liquid, an additional force, or in hydraulic terms, an additional pressure, is required. That additional pressure is known as the acceleration head. Similarly, when the piston slows down near the end of its stroke, the liquid must also slow down. Again, pressure changes are required to decelerate the moving liquid. Therefore, acceleration head continuously changes throughout one revolution. It is maximum at certain crank angles, zero at others, and changes direction during suction and discharge. This is a dynamic phenomenon. Unlike friction loss, which mainly depends on average flow velocity, acceleration head depends on instantaneous piston acceleration. That is why engineers perform acceleration head calculations separately while designing reciprocating pump piping systems. Ignoring acceleration head may lead to low suction pressure, cavitation, valve damage, pipe vibration, pressure pulsations, reduced pump life, and sometimes complete pump failure. Therefore, acceleration head is one of the most important hydraulic parameters considered during reciprocating pump design. Before we understand what is happening inside the pump, let's consider a simple everyday example. Imagine you're riding a bicycle. When the bicycle is stationary and you want to increase its speed, you have to pedal harder. In other words, you need to supply energy to accelerate the bicycle because it has mass and inertia. Now suppose you want to slow down. Instead of pedaling, you apply the brakes. As the bicycle decelerates, its kinetic energy is gradually lost, mainly as heat due to braking and friction. So, whenever an object accelerates, energy is required, and whenever it decelerates, that energy is reduced or dissipated. Exactly the same principle applies inside a reciprocating pump. Now let's observe the animation. Notice that the piston does not move at a constant speed. Because it is driven by a crank and connecting rod mechanism, its velocity continuously changes during every revolution. At the beginning of the stroke, the piston starts from rest. As the crank rotates, the piston accelerates, and its velocity gradually increases. Around the middle of the stroke, the piston reaches its maximum velocity. After that, it starts slowing down, and at the end of the stroke, it again comes to rest before reversing its direction. Since the liquid inside the suction or discharge pipe is directly connected to the piston, the liquid column must follow exactly the same motion. When the piston accelerates, the liquid must also accelerate. Just like the bicycle, additional energy is required to accelerate the liquid because it has mass and inertia. In a pumping system, this additional energy appears as an increase in pressure head, known as the acceleration head. Similarly, when the piston slows down, the liquid also decelerates. The energy required for acceleration reduces, and therefore the acceleration head also decreases. This process of acceleration and deceleration repeats during every revolution of the crankshaft, causing the pressure inside the suction and discharge pipes to continuously rise and fall. Another important observation is the effect of pump speed. As the pump RPM increases, the piston accelerates and decelerates more rapidly. This means the liquid requires even more energy to change its velocity, resulting in a higher acceleration head. This is why high-speed reciprocating pumps require careful hydraulic design. Engineers often install air vessels or pulsation dampeners to reduce pressure fluctuations, improve suction conditions, and minimize the risk of cavitation. In the next section, we'll learn how engineers calculate acceleration head mathematically and how these calculations are applied in the design of real industrial pumping systems. Now that we understand the concept of acceleration head, let's see how engineers estimate it during the design stage. API 674 provides this simplified equation to calculate the acceleration head in the suction line. The acceleration head is equal to the suction pipe length multiplied by the liquid velocity, multiplied by the pump speed, and multiplied by a pump constant. The entire product is then divided by the liquid compressibility factor and the acceleration due to gravity. Let's briefly understand each parameter. Phi represents the acceleration head, which is expressed in meters or feet of liquid column. L is the length of the suction pipe. A longer suction pipe contains more liquid, so the pump has to accelerate a larger liquid mass during every stroke. As a result, the acceleration head increases. V is the average velocity of the liquid in the suction line. Higher liquid velocity means greater inertia, which also increases the acceleration head. N represents the pump speed in revolutions per minute. As the pump speed increases, the piston accelerates and decelerates more rapidly, requiring additional pressure to accelerate the liquid column. C is a constant that depends on the pump type. For a simplex single-acting pump, the value is 0.4, while for a simplex double-acting pump, it is 0.2. K is the liquid compressibility factor, and its value depends on the type of liquid being pumped. Finally, G is the acceleration due to gravity, which is 9.81 meters per second squared. In an actual engineering project, these values are not assumed. They are obtained through collaboration between the process engineering team and the pump vendor. The process department provides information such as the fluid properties, flow rate, suction piping layout, pipe diameter, and pipe length. The pump vendor provides pump-specific information, including the pump type and operating speed. By combining all these inputs, engineers calculate the acceleration head to evaluate the hydraulic performance of the suction system. This calculation helps verify that sufficient inlet pressure is available and ensures that the pump operates safely without cavitation, excessive pressure pulsations, or vibration. Although this is a simplified equation, it serves as an excellent first check during the design stage and helps engineers identify potential hydraulic issues before the system is built. Let's now understand the flow characteristics of reciprocating pumps. Unlike centrifugal pumps, reciprocating pumps do not deliver a constant flow. Instead, the discharge flow continuously rises and falls during each piston stroke. If we plot the flow rate against time, the resulting graph appears as a series of pulsating waves rather than a straight line. This happens because the piston speed itself is continuously changing. When the piston moves slowly near the beginning and end of the stroke, the instantaneous flow rate is relatively low. As the piston approaches the middle of the stroke, where its velocity is highest, the flow rate also reaches its maximum value. Therefore, although the average flow rate over one complete revolution remains constant, the instantaneous flow rate keeps changing. These pulsations create several engineering challenges. They generate fluctuating pressures inside the piping system. They introduce vibration. They produce dynamic loading on valves and pipe supports. They increase fatigue stresses. And they may also affect the performance of downstream equipment. This is why reciprocating pumps are almost always installed with pulsation control devices such as air vessels or pulsation dampeners. These devices smooth the flow, reduce pressure fluctuations, and improve the overall hydraulic performance of the pumping system. Now let's discuss the parameters that influence the magnitude of acceleration head. Understanding these factors is essential because they directly affect pump reliability and piping design. The first factor is pipe length. The longer the suction or discharge pipe, the greater the mass of liquid that must be accelerated. Since acceleration head is directly related to the mass of fluid, increasing pipe length increases the acceleration head. This is why engineers always try to keep suction piping as short as practically possible. The second factor is fluid velocity. Higher liquid velocity means greater momentum. As velocity increases, a larger pressure difference is required to accelerate or decelerate the liquid. Therefore, acceleration head also increases. The third factor is pump speed, or RPM. This is one of the most significant parameters. As pump speed increases, piston acceleration increases rapidly. Because acceleration is proportional to the square of angular velocity, even a small increase in RPM can produce a much larger increase in acceleration head. This is one reason why high-speed reciprocating pumps require more careful hydraulic design. The fourth factor is pump type. Single-acting pumps generally produce larger flow pulsations because pumping occurs only during one stroke. Double-acting pumps distribute the flow more evenly, reducing pressure fluctuations. Triplex and quintuplex pumps provide even smoother flow because multiple pistons operate with phase differences. Finally, pipe diameter also plays an important role. Smaller pipe diameters produce higher liquid velocities for the same flow rate. Higher velocity leads to greater acceleration head. Therefore, selecting the correct suction pipe diameter is extremely important in reciprocating pump installation. Now let's discuss the parameters that influence the magnitude of acceleration head. Understanding these factors is essential because they directly affect pump reliability and piping design. The first factor is pipe length. The longer the suction or discharge pipe, the greater the mass of liquid that must be accelerated. Since acceleration head is directly related to the mass of fluid, increasing pipe length increases the acceleration head. This is why engineers always try to keep suction piping as short as practically possible. The second factor is fluid velocity. Higher liquid velocity means greater momentum. As velocity increases, a large so important from an operational perspective. One of the first consequences is a reduction in suction pressure. During the suction stroke, part of the available pressure is consumed in accelerating the liquid column. As a result, the actual pressure at the pump inlet decreases. If this pressure falls below the liquid's vapor pressure, vapor bubbles begin to form. This phenomenon is known as cavitation. Cavitation is one of the most destructive problems encountered in reciprocating pumps. When these vapor bubbles travel into regions of higher pressure, they collapse violently. The collapse generates localized shock waves that can damage valve seats, cylinders, plungers, and other internal components. Apart from cavitation, excessive acceleration head also causes pressure pulsations. These pulsations generate vibration throughout the piping system. Over time, vibration may loosen supports, crack pipe welds, damage instruments, and shorten equipment life. The fluctuating pressures also increase the mechanical loading on suction and discharge valves, resulting in faster wear. In severe cases, excessive acceleration head may even limit the maximum operating speed of the pump. Therefore, controlling acceleration head is not just a theoretical calculation, it is a critical aspect of ensuring safe, reliable, and long-lasting pump operation. At this stage, it is important to introduce another critical concept. Net positive inlet pressure. NPIP is the actual pressure available at the pump inlet above the vapor pressure of the liquid. In simple terms, it represents how much pressure margin is available to prevent the liquid from vaporizing before entering the pump cylinder. If the inlet pressure becomes too low, vapor bubbles will form. As these bubbles collapse during the discharge stroke, they cause cavitation, leading to equipment damage and reduced performance. According to API 674, the minimum pressure in the suction line, measured before any impedance improving device such as an air vessel, must always remain above the vapor pressure of the pumped liquid with an adequate safety margin. Acceleration head directly influences NPIP. During the suction acceleration period, the pressure drops because additional energy is required to accelerate the liquid. Therefore, engineers must carefully evaluate the combined effects of static suction head, friction losses, vapor pressure, and acceleration head while designing the suction piping. If sufficient NPIP cannot be maintained, corrective actions such as reducing pump speed, increasing suction pipe diameter, shortening the suction line, or installing an air vessel may be necessary. Ensuring adequate NPIP is one of the most important requirements for achieving reliable reciprocating pump operation without cavitation. Now that we've understood the causes and effects of acceleration head, the next question is, how do engineers reduce its impact in real industrial systems? The answer lies in proper hydraulic system design. The first and most important consideration is suction pipe sizing. A larger suction pipe reduces the velocity of the liquid. Since acceleration head is directly proportional to the liquid velocity, reducing velocity immediately reduces the acceleration head. That is why API 674 recommends keeping suction line velocities relatively low compared to discharge lines. The second consideration is pipe length. Remember that acceleration head depends on the mass of liquid inside the pipe. Longer pipes contain more liquid, which means more mass must be accelerated during every stroke. Therefore, wherever possible, engineers keep the suction piping short and direct. Another important point is to avoid unnecessary elbows, tees, strainers, and sudden changes in pipe direction. These fittings increase friction losses and disturb the flow pattern. When friction loss combines with acceleration head, the suction pressure may fall below the liquid's vapor pressure, leading to cavitation. Pump speed is another major design parameter. As we discussed earlier, acceleration head increases approximately with the square of pump speed. This means that increasing the pump speed from 300 revolutions per minute to 600 revolutions per minute does not simply double the acceleration head, it increases it by nearly 4 times. For this reason, engineers always verify the allowable operating speed during pump selection. Finally, when acceleration head cannot be reduced sufficiently through piping design alone, engineers install special hydraulic devices such as air vessels and pulsation dampeners. These devices significantly improve the hydraulic performance of reciprocating pump systems. One of the most effective methods of reducing acceleration head is the installation of an air vessel. An air vessel is simply a pressure vessel containing compressed air above the liquid level. It is normally installed as close as possible to the suction or discharge nozzle of the reciprocating pump. Let's understand how it works. During the portion of the stroke where the piston demands a high flow rate, the air inside the vessel compresses slightly and supplies additional liquid to the pump. During the portion of the cycle where the flow demand decreases, the vessel refills. This continuous expansion and compression of the trapped air smooths the flow entering and leaving the pump. As a result, instead of accelerating the entire liquid column inside a long pipe, the pump only accelerates the relatively short column between the pump and the air vessel. Since the effective pipe length becomes much smaller, the acceleration head decreases significantly. The benefits of installing an air vessel include reduction in acceleration head, improved net positive inlet pressure, reduced cavitation risk, lower vibration levels, reduced pressure pulsations, less valve wear, longer equipment life, and lower power consumption. Because of these advantages, air vessels are widely used in high-pressure reciprocating pump installations throughout the oil and gas, refinery, chemical, and water industries. Another important device used in reciprocating pump systems is the pulsation dampener. Although both air vessels and pulsation dampeners reduce pressure fluctuations, their operating principles are slightly different. A pulsation dampener is specifically designed to absorb pressure spikes generated by the reciprocating motion of the piston. Inside the dampener, energy is stored temporarily in a compressed gas chamber, spring mechanism, or flexible diaphragm. Whenever a pressure spike occurs, part of the hydraulic energy is absorbed by the dampener. When the pressure decreases, this stored energy is gradually released back into the system. This process smooths the pressure waveform and significantly reduces pressure pulsations. Several types of pulsation dampeners are commonly used in industry. The first is the bladder type, where a flexible rubber bladder separates the gas and liquid. The second is the diaphragm type, where a flexible diaphragm performs the same function. The third is the spring-loaded type, which uses mechanical springs instead of compressed gas. Selection depends on the operating pressure, fluid properties, maintenance requirements, and system design. By reducing pressure pulsations, pulsation dampeners improve system stability, reduce vibration, protect instrumentation, extend valve life, and improve overall pump reliability. Today, pulsation dampeners are considered essential components in many API 674 reciprocating pump installations. Let's summarize the key points we've discussed throughout this presentation. A reciprocating pump produces pulsating flow because the piston continuously accelerates and decelerates during every revolution. As the piston changes its velocity, the liquid inside the suction and discharge pipes must also accelerate and decelerate. Since the liquid possesses mass and inertia, additional pressure is required to produce this acceleration. This additional pressure is known as the acceleration head. Acceleration head depends on several factors, including pipe length, pipe diameter, liquid velocity, pump speed, crank angle, and pump configuration. If acceleration head becomes excessive, it reduces suction pressure and increases the risk of cavitation. It also generates pressure pulsations, vibration, valve wear, and mechanical fatigue. To minimize these problems, engineers use proper suction pipe sizing, shorter piping layouts, lower operating speeds where appropriate, air vessels, and pulsation dampeners. Maintaining adequate net positive inlet pressure while controlling acceleration head is one of the most important objectives in reciprocating pump hydraulic design. Understanding these principles helps engineers design safer, more efficient, and more reliable pumping systems. Let's summarize the key points we've discussed throughout. That brings us to the end of this presentation. I hope this session has helped you understand not only what acceleration head is, but also why it plays such an important role in reciprocating pump design. Whether you're a student, a mechanical engineer, or a rotating equipment professional, understanding acceleration head is essential because it directly influences pump reliability, cavitation, piping design, and overall system performance. If you found this presentation useful, I encourage you to continue exploring reciprocating pump hydraulics, API 674 design principles, and practical pump engineering concepts. Thank you very much for your time and attention. I look forward to seeing you in the next presentation.